everyone, I'm Professor Harrison, and welcome back to our module on regression. Today we're going to be deriving the OLS formulas for simple regression, the formula for the slope and the formula for the intercept. We're following Margot, a graduate student piecing together the story her family buried, using regression to make sense of a box of old letters, a stack of published articles, and her family's old account statements. Last time she figured out that the best fitting line is the one that makes the squared misses as small as possible. Today she wants to figure out the formula that produces that line directly. And she's got something real to try it on. It's Victor's fund, and how its returns move with the market month by month. She pulls up another page from her grandfather's fund records. So last time we landed on the OLS criterion. The best fitting line is the one that makes the sum of squared residuals as small as possible. We also said that finding it is an unconstrained optimization problem. We're choosing two numbers, the intercept and the slope, that minimize a function. Today we're actually going to solve that problem to get the formulas. Here's the setup. The sum of squared residuals is a function of the intercept and the slope. To minimize a function, we do what we always did in the calculus module. We take the derivative and set it equal to 0, then solve. The only twist is that we've got two unknowns now. So we take two partial derivatives, one with respect to the intercept and one with respect to the slope. We set each of them equal to 0. And those two equations are the first order conditions, and together they're going to pin down the minimum. I'll spare you the algebra of grinding through them, but the result is pretty clean and worth seeing where it lands. Let's start with the slope. The OLS slope estimator ends up being the sum over all the points of x minus its mean times y minus its mean divided by the sum of x minus its mean squared. Now let's look at what those two pieces are doing. The top is measuring how x and y move together, and the bottom is measuring how much x moves on its own. If you then divide both the top and the bottom by the number of observations, then you get something that we've seen before. The top becomes the covariance of x and y, and the bottom becomes the variance of x. Both of these are straight out of the probability module. So the slope is really just the covariance of x and y divided by the variance of x. The line tilts according to how much x and y co-move, scaled by how spread out x actually is. The intercept is a little bit easier. Once you have the slope, the intercept is just the average of y minus the slope times the average of x. And this formula tells us something pretty nice. If you plug in the average x, the line hands you back exactly the average y. So the OLS line always passes through the point of the averages, the average x and the average y. No matter what your data looks like, the best fit line is always going to end up running right through the center of the cloud. So let's put it to work. Margot's got Victor's fund. For 5 months, she's lined up two numbers, the market's excess return for that month and the fund's excess return for that month. She wants the line that best explains the fund's return from the market's return. This particular setup, regressing an investment's excess return on the market's excess return, is common enough that it's got a name and is called a market model. And the slope that it produces is the fund's beta. Here are the 5 months. The market's excess returns are 1, 2, 3, 4, and 5%, and the fund's excess returns are 5, 4, 5, 8, and 13%. First, we need the means. The market returns average out to 3%. The fund returns average out to 7%. So our average x is 3 and our average y is 7. Now we do the slope. We need for each month the market return minus its mean of 3 and the fund return minus its mean of 7. For the market, those deviations are minus 2, minus 1, 0, 1, and 2. For the fund, they're minus 2, minus 3, minus 2, 1, and 6. We multiply them month by month. Minus 2 times minus 2 is 4, minus 1 times minus 3 is 3, 0 times anything is 0, 1 times 1 is 1, and 2 times 6 is 12. When we add those up, we get 20, which is the top of our slope formula. For the bottom, we square the market deviations. 4, 1, 0, 1, 4. Those add up to 10. So the slope is 20 over 10, which comes out to 2. And the y-intercept is the average y minus the slope times the average x. That's 7 minus 2 times 3, which is 7 minus 6, or 1. So Margot's best fit line ends up being the fund return equals 1 plus 2 times the market return. Let's read that line. The slope is 2. That's the fund's beta. It says that for every 1% that the market moves up or down, the fund tends to move about 2% in the same direction. The fund is twice as sensitive to the market as the market is to itself. The intercept is 1. That's the fund return when the market does nothing. It's the piece of the return that has nothing to do with the market at all. And here's the practical payoff of having the formula instead of eyeballing it. If a new month comes along and the market is up 3%, Margot doesn't have to guess. She can read it straight off the line. 1 plus 2 times 3 is 7. The line says that the fund should be up about 7% in this case. So when the market shifts, the beta of 2 tells her exactly how much to expect the fund to shift along with it. That's the decision rule that the slope hands her. Margot sits back. 1% a month. That's the part of Victor's return that the market doesn't explain. His own edge, clean and steady, at least in those early years of his fund. The number stops her because she's seen it before. Not in the fund records, but actually in one of Bess's articles. Years ago, long before the rest of this started, Bess had written a short piece of a promising young fund manager beating the market by about 1% a month. She named Victor as one to watch. Margot had read straight past it the first time, just background, but it's the same number. It's the edge that first put Victor on Bess's radar, and it's the one that Margot just pulled out of his own books by hand. So that's where the OLS formulas come from. We took the sum of square residuals and set its two partial derivatives equal to 0, then solved. The slope ends up being the covariance of x and y over the variance of x. How the two move together scaled by how much the input varies on its own. The intercept is just the mean of y minus the slope times the mean of x, which is exactly what guarantees that the line runs through the center of the data. Two formulas straight out of the criterion that we set up last time. Now we can fit any line without any guesswork at all.